Hi, welcome to the Unit 1.4b video. In this video, we're going to focus on limiting reactant and theoretical yield, which is aligned with the first half of key question 2. You don't have a note packet with this, so you can take notes on a separate sheet of paper. Maybe for you, you just want to watch the video and just write down some notes. Maybe you want to actually solve the problems along with the video. The choice is yours. If you would like a note packet, just let me know. In addition, there will be videos that were linked at the very end of part 2 of this video. This is just the first half, which will provide additional support and resources. All right, so we're focusing on limiting reactant and theoretical yield, and one of the best ways of grounding ourselves in that is to use the chemistry and cooking analogies, where we see our balance equation is like our recipe. It tells you the ratios of reactants, which are like your ingredients, and products, which are like your food. The other term we use a lot is limiting reactant or reagent. It's the same thing. And that's the reactant that you will run out of first. So remember, reactants are like an ingredient. So whatever ingredient you run out of first, that's what you're limiting. And theoretical yield is the maximum amount of product or food you can make. So these are the terms that we use in these types of problems. So before we begin, I want you to sort of, we're going to use like sort of this grilled cheese scenario. And I want you to sort of picture a scenario where you're sitting at home and you get a call from a few friends and they're like, hey, we're hungry and we're coming over and we want to play Fortnite. And you're like, what? So you're like, all right, let me go check to see what I have in my kitchen since these folks are coming over and they're going to be hungry. Okay, you look and you say, oh, great, I got 10 slices of bread. Oh, and I've got 7 slices of cheese. You're like, you know what? I can make some dope grilled cheese sandwiches with this. Yes. So what are the questions that may come to mind then? First of all, you need your recipe. And because they came out the last minute, you're not going to make a fancy grilled cheese sandwich. They're going to get 2 slices of bread and 1 slice of cheese to make 1 grilled cheese. The other thing you may be wondering is like, which of these ingredients am I going to run out of first? Or what's the maximum amount of food I can make with these ingredients? These are the same sort of questions that a chemist asks. So when a chemist goes into a lab and they're going to synthesize something through a chemical reaction, some of the things they want to know is from the reagents that they're using, the amount that they're deciding to use, which one of these will run out first? Which reactant or reagent will run out first? What's the most amount of products I can make, right? So these are the same sort of questions that they would ask. All right, so let's tackle that first question. Which ingredient will run out first? The limiting reactant or reagent question. There are 2 methods to doing this. The first method, method A, is when you're comparing the reactants together. So for this, we don't really need to look at the products anymore. We just want to focus on the reactant side. And we have 2 reactants here, bread and cheese. So let's start off with the bread. We could ask ourselves, for the 10 slices of bread, how many slices of cheese do I need? And the recipe will help you determine that. So for 2 slices of bread yields 1 slice of cheese. That means for 10 slices of bread, you would need 5 slices of cheese. All right, so you know that you need 5 slices of cheese. Go back and figure out how much you have. So you go in your kitchen, you're like, I have 7 slices. So what does that tell you? You have more cheese than you need, so the cheese is in excess, which makes the other one the limiting. So the bread becomes limiting. You could alternatively do this by focusing on the cheese instead of the bread and say, well, for the 7 slices of cheese, how many slices of bread do I need? And according to your recipe, 1 slice of cheese is 2 slices of bread, so that's double the amount. So that would mean for 7 slices of cheese, you need 14 slices of bread. All right, you need 14. Go back, see how much you have. You only have 10, so that tells you the bread is going to run out first. The bread is your limiting. Let's try the same sort of thing with a chemical reaction. So what is the limiting reactant if you combine 12 moles of N2 and 20 moles of H2? We want to figure out which one of these is going to run out of first when we mix the 2 of them together in this reaction described by this balanced chemical equation. Okay, so I'm going to pick one reactant to focus on first. Let's start off with the 12 moles of N2. And so I can ask myself, well, for the 12 moles of N2, how many moles of H2 do I need? Okay. Now here's where dimension analysis comes in and is super duper handy. What we're essentially trying to do, let's take a step back. We're essentially just trying to convert from 12 moles of N2 to moles of H2. So I'm going to start with what I'm starting with, which is 12 moles of N2. And then I'm going to use the balanced chemical equation to get my conversion factor. Since I'm only focusing on N2 and H2 in this question, I'm just going to look at the N2 and H2 part. So there's, according to the balanced chemical equation, there's an invisible 1 here. So there's 1 mole of N2 and 3 moles of H2. I'm going to write that as into a conversion factor fraction. The question is what should go on top and what should go on the bottom. Should the 1 mole of N2 go on the bottom or the 3 moles of H2 go on the bottom? That's right, the 1 mole of N2 should go on the bottom because we want to cancel out moles of N2, and the 3 moles of H2 should go on the top because we want to keep it. Once we have our setup, we can go ahead and do the math, and we get that we would need 36 moles of H2. All right, we go back and we know that we need 36 moles of H2. Let's go back and figure out how much we have. We have only 20, and the problem tells you what you have. That's super important to note. Problem tells you what you have. The problem tells you what you have. So you only have 20 moles, so that means that you have less than what you need, so H2 is eliminating. We could do the same sort of thing with H2. We don't have, you should only do one, but let's just show you what it would look like if we started with H2 instead of with N2. So, but it's the same thing. We start with 20 moles of H2, and we're trying to figure out how many moles of N2 you need for the 20 moles of H2. All right, we're going to use dimensional analysis to help us do the math to figure this out. So 20 moles of H2 over 1. Since we're focusing on H2 and N2, again, we're focusing on the reactant side here. What goes on the bottom in this case is that the 3 moles of H2 or the 1 mole of N2. All right, the 3 moles of H2 should go on the bottom to cancel out, and 1 mole of N2 goes on top. And that gives us about 6.7 moles of N2. So this is what you need. Go back and figure out how much you have. The problem tells you what you have. The problem tells you what you have. All right. So you see that the problem tells you you have 12 moles of N2. You need 6.7 moles. Well, you have more than you need. So that means N2 is in excess and H2 is eliminating. Remember, you only need to do one of these. You could either figure out how many moles of H2 you need for the 12 moles of N2, or you could do how many moles of N2 you need for 20 moles of H2. You don't have to do both. Just one is enough to give you your limiting. With that being said, I want to emphasize one more time, because I think this is super important. Kids always make this mistake. Remember, the information in the problem tells you what you have or need. Have, that's right. And what you solve for is what you need. That's super duper important. The problem tells you what you have. Okay. All right, let's move on to method B. For method B, we again are trying to figure out which ingredient runs out first, limiting reactant. But in this method, instead of comparing the two reactants, we're going to determine the amount of product or food we can make for each reactant or ingredient. So using the grilled cheese analogy first, just to sort of ground us in what we're doing, that would look like this. We would try and figure out, well, for the 10 slices of bread, how many sandwiches I can make, and for the 7 slices of cheese, how many sandwiches I can make. All right, starting with 10 slices of bread, looking at the ratios, it's a 2 to 1, so we know we can make 5 sandwiches. And for the cheese, it's a 1 to 1, so we know we can make 7 sandwiches. Okay, so the amount of bread we have will only give us 5 sandwiches, and the cheese will give us 7. So what's our limiting there? The answer is the bread, and we base it on the fact that it gives us the smallest amount. So the one that gives you the smallest amount of food or product is your limiting reactant. I'll say that again. The one that gives you the smallest amount of food or product is your limiting reactant. And that's because you can't make more than you have. We're going to run out of the bread, which is what a limiting reactant is. It runs out first. We're going to run out of the bread first before we can make those additional 2 sandwiches. So bread is our limiting. The same sort of thinking we can do in method B for a balanced chemical equation like this. So again, we're going to figure out, well, for 12 moles of N2, how much NH3 I can make. And we're going to use dimensional analysis to do that math. So we're going to figure out for N2 how much product we can make, and then later we'll do for H2 and figure out how much product we can make. All right, starting with N2, we have 12 moles of N2. What do you think your conversion factor will look like? What's important for this problem? Well, we want to go from N2 to NH3, so these are the things we'll be using, 1 moles of N2 and 2 moles of NH3. What goes on the bottom in this case? Is it the N2 or the NH3? That's right, 1 mole of N2 goes on the bottom and 2 moles of NH3 goes on the top. Once you have your setup, you can quickly do your math, and you discover that for 12 moles of N2, you can make 24 moles of NH3, which makes sense because it's a 1-to-2 ratio. So 1 of this will give you 2 of that. That means that 12 moles of this will give you 24 moles of that. All right, let's try the same thing now with H2. So for 20 moles of H2, I want to figure out how many moles of NH3 do I need. All right, cool. So, or sorry, I can make, not need. How much moles of NH3 I can make. So we're going to set it up, 20 moles of H2. What do you think what goes on the top of this conversion factor? That's right, 2 moles of NH3 and 3 moles of H2, which again we got from the balanced chemical equation, goes on the bottom. We can do our math, and that will give us that we can make 13.3 moles of NH3. All right, now, based on this information, which one is our limiting reactant? Are you going to choose the reactant that gives you the most amount of product or the one that gives you the least? That's right, it's going to be the least amount of product because you cannot make more than you have. So H2 in this case is limiting because it gives you the least amount of product. Okay. In the case with method B, you have to do both. You have to do both equations. Why? You need to be able to compare the amount of product you can make from both reactants. So that's why you have to do them both. So 12 moles of N2, how many moles of NH3? And for 20 moles, how many moles of NH3? So you must do both of them. One last time. Remember, the problem tells you what you have. That's super duper important. So what you have is in the product. And here, when you're doing method B, you're solving for how much you can make from those. Okay, problem tells you what you have. All right, cool. We're going to pause this video now, and then in part 2, you're going to see theoretical yield. Hope you found this video helpful. Have a quality day.